NASA headquarters. So, John, please get us started.
Well, thank you very much, Ellen, and welcome everyone to our session on the search for life in the universe. We are entering a new realm in our search to answer the question, are we alone? And today we're here to tell you a bit of a grand story. Thanks to investments in technology, we have pushed the limits of our most creative scientists and engineers and are about to take a big leap in our quest to unravel the mysteries of the universe. That next big step is the James Webb Space Telescope. And we love drama at NASA. Coming in 2018, October 2018 in fact, the James Webb Space Telescope will transform our view of the universe. In Space 2018. Now 400 years ago, our mission is to innovate, explore, discover, and inspire. And I hope today that's our main purpose, is to inspire all of you to be along our path to try and unravel these mysteries and perhaps to find out the answer to the question, are we alone? And that's really the key. We've made enormous technical advances, and you're going to hear from our speakers that we are on the cusp, perhaps the next generation, to be able to answer that question, are we alone, from a scientific progression. Galileo started it all 400 years ago when he turned the telescope not from the Italian reconnaissance organization, but to look at the skies, and in fact invented telescopic astronomy. And from there emerged a great scientific renaissance. In our time, the Hubble Space Telescope, deployed by Charlie Bolden in 1990 and repaired by me a few times, the Hubble has really transformed our view of the universe, and not just for scientists, but I think for everybody on planet Earth. It's opened frontiers in virtually all areas of not only astronomy, but many areas of fundamental physics. Today, we're going to present to you a little bit of the history of the universe, but it won't take 13.72 billion years to describe. But I find it amazing that with relatively small telescopes, the Hubble is a 2.4 meter telescope in Earth orbit, we've been able to piece together almost this entire history of the universe, from just a few 100 million years after the Big Bang to the evolution of stars, galaxies, planets, our own planet, and the solar system that we live in. John Mather will describe this in more detail. Finding Earth's twin. That's kind of the holy grail. That doesn't mean the only place that we might find out whether there's life elsewhere besides planet Earth. But the Kepler telescope has discovered thousands of new planets and has found out, as you heard, that there are probably billions of planets like Earth in our own solar system. This is a picture of a system that Kepler discovered, Kepler 62, and in that system are several planets that could live in a so-called habitable zone where liquid water would exist, trying to look for life that's familiar to us. And Sarah Seeger will describe that in some more detail. What are we looking for? This is science. We're not looking for what Charlie and I might have been looking for on orbit, which were aliens coming to visit us. We're looking for signs of life on a planet around a nearby star. And what those signs might look like. Well, if we were looking at Earth, we would see signs of our sky, our blue sky. We would see signs of oxygen, of carbon dioxide, of sulfur dioxide from volcanoes, and we might even see signatures that there was plant life. And we see that by dissecting the light into its component colors. And Sarah will describe that in some more detail. Spectroscopy. Occasionally we have a chance alignment of a planet with its star, and light passes through the atmosphere. And it's some of that light that we can look at that will tell us about the characteristics of the planet. It's called a transit or transit spectroscopy. The James Webb Space Telescope may allow us to detect the presence of water around a very large planet, a rocky planet, a water world. To go the next steps, we want to look for biosignatures, not just of liquid water, but of the gases in the atmosphere, and perhaps leading to the discovery of life. Our investments may transform the way we approach this. The Space Launch System, for example, could provide us the capability to launch a much larger complex telescope, or perhaps to go investigate Europa. And instead of taking 7 years to get there, we could get there in an express of perhaps 3 or less years. We've seen some amazing things in our solar system. This is a view of part of Saturn and Saturn's rings from the Cassini spacecraft. And if you look closely, you see this pale blue dot. That's the Earth from 900 million miles away. Pretty amazing. It doesn't look like much, but by analyzing the light of the Earth from this distance, we can learn something about the planet, and Sarah will talk more about that. So we have a progression. We have a roadmap or a path that we're trying to take, and it started with ground-based observatories and the 1995 discovery that we live in a universe that has other planets in it. Originally, we thought there were only 9 planets. Of course, then we were demoted to 8 planets. But with Hubble, the Spitzer, and the Kepler telescopes, we've really transformed our whole view of the universe. And Sarah will talk about that, but such that we now know that we live in a galaxy and a universe filled with planets. We're working on the Transiting Exoplanet Survey Satellite, which will survey our nearest neighbors. The James Webb Space Telescope, which will allow us to study those neighbors in great detail. We're also working on concept studies, and you'll hear from Dave Gallagher about that, of the WFIRST/AFTA telescope. And in the decadal survey was outlined a New Worlds telescope, a telescope of a new generation that might be able to actually answer that question, are we alone in the universe? These are not just dreams. This is what we do at NASA. We queue up things that some people say are impossible or that are dreams, and we make them reality. And with that, I'll hand it over to Dr. Mather.
Well, thank you. Is this working? I want to tell you about how we're doing on the James Webb Telescope itself, and to show you how it fits into the grand scheme of getting ready to discover life around other planets, if it's actually out there. So I've been a telescope builder all my life, because when I asked my dad when I was about 6 years old, how did we get here? Nobody knew. So how do you find out? You build telescopes. So I want to show you how we're doing it. So with our first chart here, I have an illustration from Edwin Hubble. That's him sitting with the big telescope, the Mount Wilson, out in California. It's a 100-inch telescope, basically the same size as the Hubble telescope that we now have in space. It took us more or less a century to catch up with being able to put stuff in space. He was able, with that telescope, to make that little picture that we saw on the lower right, which is a picture of the galaxies, how far away they are, and how fast they're going. So he was the first one to really know that this picture was correct, though a few other people had predicted it. But this was the discovery of the expanding universe. If somebody talks about the Big Bang Theory and they think it's kind of silly, well, we were forced into this. We saw it happen in 1929, and people were stunned. This was front page news around the world, and we've been living with it and trying to understand it ever since. It's a very strange and amazing story, but it seems to be true. So we haven't got a better story. So now we are continuing the trend about building better and bigger telescopes, and trying to figure out what else is out there. So here we have let's see if this is going to come out, a picture taken with the Hubble Space Telescope as the background, and here is the capsule history in the graphic. So, by the way, on this chart are 2 discoveries that earned Nobel Prizes. One is the little map that's on the left-hand side. You see that little green and blue speckly pattern. That was what was discovered by the Cosmic Background Explorer satellite and led to that prize of 2006 for our team. There's another one on here, which is 9 billion years later, where it says dark energy and accelerated expansion. That was discovered based on the Hubble Space Telescope as well. We now know there's something called dark energy, which means we don't know what it is, which is causing, quote, the universe to expand at an accelerating rate. So there's still plenty of mysteries on this chart. We have an idea about how this whole thing works. We have recognized evidence for dark matter in the universe, much more abundant than ordinary matter, and this story is pretty spectacular. Not to say proven completely, but it matches astonishingly well with the observations that we have. So we claim from the story that we're telling here and the formulae that go with it that we know the details of the universe within a few % accuracy, which is really a truly stunning accomplishment for modern science, and it is entirely based on space astronomy that we have initiated here at NASA. So among the things to point out here are that the first stars probably formed about 400 million years after the expansion began. I would also like to point out that the Big Bang that we describe as a Big Bang is not like a firecracker going off in the corner, but is actually an infinite universe expanding into itself, probably without a beginning, although we talk about the beginning, and probably without an end. So this is something we don't know, but sure would like to know. So going on to tell you more about it, there's little Earth over there on the right. We're newcomers. We have been here for about 1/3 of the age of the universe. 4.5 billion years for the age of the Earth, 13.5 for the age of the universe. So now I want to show you a nebula, which is somewhat like the nebula that we live in, the Milky Way galaxy. As you know, a galaxy is made of hundreds of billions of stars orbiting a common center, held together by gravity. Some of that gravity comes from dark matter, by the way, and we wouldn't be here without it. So if anybody thinks, well, dark matter, that's just an amusing thing those astronomers thought up, we wouldn't be here without it. So lots of wonderful things for us to find. If the sun were in that galaxy, we would be somewhere out on the outer edge, and we would be able to look in towards the center, and we would wonder what it was like, because we live in the plane of our Milky Way galaxy, which is about as flat as a CD, and so you can barely see the structure of it when you live inside it. So we have to look at other people's galaxies, if there are indeed people out there, to think about what does it look like to be who we are. Anyway, so one of the great mysteries is how does this happen? How do galaxies like that come to be? So we have statistical calculations of what the early universe was like, put it into a computer, simulate the action of gravity operating on the dark matter and the ordinary matter, and accounting for the cosmic dark energy that causes acceleration. So this is a simulation of early universe. You see gravity is pulling the material back together. By the way, the simulation has subtracted out the fact the whole universe is expanding. So it's taken that viewpoint. Now you can see galaxies beginning to light up with explosions. This is a totally spectacular process. We have black holes forming and drawing in material, sending out jets of immense intensity. All of these things happened in the early universe much more frequently than they do today. If there were people or intelligent beings back there to witness this event, it would have been a very, very spectacular event for them to think about. By the way, there were chemical elements of life being produced in these explosions, so we could imagine that life was possible within a few 100 million years of the original expansion. So here we're running along to the universe is almost 9 billion years old in this simulation, and it begins to settle down, and that's an interesting time because that's about when the solar system was formed also. Here it's beginning to settle down. The universe becomes quiescent, and the solar system forms. So imagine, if you could, that we tell whether this picture is true. How would you know if it's true? We take snapshots of the picture, of the movie, and you compare the snapshots with the snapshots of the sky that we can make with the Hubble telescope and the successor telescopes that we are now building. So that's a great mystery for us. We are on the trail of figuring out if it's true. So By the way, this simulation was called the Illustris, and it's just current this very year. So now I show you a picture of the thing that you would think of as a star. If you look at the middle star of the Sword of Orion, this is it. This is not a single star. This is a cloud of glowing gas and dust with hundreds and hundreds of bright new stars born in there very recently, shining beautifully. This is where astronomers always turn their new telescopes to see what's most beautiful and most scientifically interesting, because it's one of the places where stars are being born in great abundance today. By the way, there's about 5 or 10 new stars per year being born in our Milky Way, and so it's something we have plenty of to study. Presumably some of those have planetary systems with them, one of the great opportunities for us with the Webb telescope. So now I want to talk about how did we get started with the James Webb telescope in particular. So back in 1995, Alan Dressler chaired a committee that recommended two things. One was to build a telescope like the one that we're building. It wasn't called James Webb Telescope back then, of course. And they said the other thing they said was develop the technology to find Earth-like planets around other stars. So we've been doing that. Now, in that day, we had no idea how many of them there would be. So we didn't know how hard the project would be. We have made immense progress, both on the technology, which Dave will tell you more about, and on knowing how hard the job is. We know there are billions of planets out there, and they're not all far away. So this is definitely a good step forward. So our project was endorsed twice by the National Academy of Sciences. They do a survey every 10 years. It was their top priority in 2000, and they built their entire survey in 2010 around it. So we're doing well with carrying out what they want us to do. And by the way, we got our first peer review when this project was announced to the Astronomical Society in 1996 by the head of NASA, Dan Golden. He got a standing ovation for the presentation. And I think that was definitely an encouraging sign that this was the project our entire user community, scientific world would like us to do. So we're doing it. This is what it looks like. And I have the logos for the 3 space agencies that are partners in this immense project. The telescope, by the way, is being built by our prime contractor, Northrop Grumman, near LA, but under supervision and direction from NASA Goddard, where I work. So I'm speaking here about this one, which is now a project of well over 1,000 people currently working on behalf of 10,000 roughly future users and all human beings who will use the data. This is a comparison of how large the telescope is compared with the Hubble. These are scale pictures. So you see on the left the mirror of the Hubble, 2.4 meters in diameter, about 8 feet. Same as Hubble, the man's telescope on Mount Wilson in 1920. On the right-hand side, you see the James Webb telescope. The mirror is about 21.5 feet, roughly the distance from floor to ceiling in here. Much larger, clearly much larger than the rocket is, so we have an immense challenge of folding it up to get it into space. The wavelength range is illustrated there on the bottom also. The telescope, the new one, overlaps the wavelength coverage of the Hubble. At the near infrared, we begin at 0.6 microns, which is about the wavelength of a red laser pointer. And we go out to 28 microns, which is a wavelength which your body emits very intensely, and you don't feel it. But you would be cold if you were out in outer space because of that radiation. So there it is. This is a sign of technical progress on the design. We require 18 hexagonal mirrors. Each is made of beryllium coated with gold. Each of them is light enough that you could lift it yourself individually, but they are so precise that they're basically perfect. So the sketch on the right-hand side shows you that if we were to expand the mirror to the size of the continental United States, the mirror would be accurate within 3 inches. So this is completely amazing technology we have now mastered and we're using. The mirrors are finished, by the way. They're all in their storage cans up at Goddard Space Flight Center. So we've got a little graphic illustrating how many there are. All 18 are done. We've measured their shapes when they're cold in the giant vacuum tank at Marshall Space Flight Center. So we're really thrilled with the mirror technology progress. This is something where my friends and colleagues laughed at me and said, "You'll never be able to do that." But we have done it, It was hard. So you have here a movie showing what the sun shield is like. The sun shield is as big as a tennis court. Imagine Roger Federer running back and forth over half of it. We have to unfold this thing from a folded condition in outer space, and so of course we've been rehearsing. So what you just saw was rehearsals with a full-scale practice layer. So it works, of course. So, okay, machine, next please. There we go. So what we have here is the instrument module has been just installed in the cryogenic vacuum tank at Goddard Space Flight Center, lowered down from a crane, and it being attached with the cables to the fixtures in the instrument chamber. This is a place where we simulate the outer space environment. The light coming from the telescope is simulated, so we will be able to tell whether this instrument package will be focused and working properly when we get to outer space. Here's another view of the same process. The dome has been lifted off the test chamber. You can see the crane lifting the instrument package down in. So we're very thrilled with this. The instruments are doing very well in their test as of this week. No surprise there. This is the next place we take the telescope to. This is the Chamber A at Johnson Space Flight Center. If you were an Apollo astronaut, you went here to practice because this was big enough for this. On the left-hand side, you see the Apollo capsule in there. Astronauts had to practice getting out of the spacecraft on land and getting off onto the surface of the moon in a vacuum. So they practiced, and it worked, of course. Now, 50 years later, we need the same chamber for another purpose. We have fitted it with cold shroud inside so it can get down to the temperature that we need for the testing of the telescope, and it turns out to be just the right size for what we needed for the Webb. So we're really thrilled that we have the equipment and we're doing the right thing. So in a little while, namely October 2018, 4.25 years from today, we will push the button and the telescope will go up on its rocket, which is, by the way, a contribution of the European Space Agency. So we'll go up and be unfolded in outer space, and this is the deployment video. It has been all carefully figured out exactly when and where we do everything. So, of course, the first thing to happen is you unfold the solar panel, need solar juice to keep the batteries from running down. Then we will unfold the telemetry dish, stay in touch with the Earth. This happens about by the time we get to the moon or past the distance of the moon. Then the last things that come out are the solar shields. Here they come. And if you look at this and you say, isn't that pretty complicated? Yeah. You should be intimidated. You should know that we have two of everything where you could possibly have two of everything, and we are rehearsing this out of town. We have done many, many practice trips with the unfolding process at the various labs we have around the country. Both cold and warm for the parts that can be tested cold. The sun shield is just too darn big. There's no way to test that in a cold tank. And certainly we cannot test it in zero gravity, so we have to think a lot. At any rate, this is complex, but it's been very thoroughly rehearsed, and we're pretty sure it will work. That's our job, to make sure. So the final steps are to pull on various cables that stretch out the sun shield and separate the 5 layers. So there it is, almost in the final shape. And finally, the mirrors themselves finally unfold. So this is what it takes to get a big telescope into a not big enough rocket. So when we have a bigger rocket, we can put up bigger stuff. Thank you for thinking about that. And of course, you can also imagine when we have astronaut capabilities in deep space, we'll be able to make sure the telescope keeps on working longer. Anyway, there it is. It's finally in the right shape. It's not focused at that point. It takes another couple of months to cool down and be focused. Anyway, this is our 2 months of terror, perhaps. But we have to make sure it works, so we do that. So just to wrap up, to show you an illustration of some of the things we're expecting to see and to tantalize you with what we'll be able to ask questions about. And this is looking back towards the earliest moments in the universe. This is an expansion of the Hubble telescope picture. Imagine that the real one is much sharper, like this, with many more galaxies in it. So this tells you that there's an awful lot more to know than what we can see today, looking back towards the earliest moments of the universe. Also, going on to things that are close to home, where stars are being born today. This is a dust cloud with a star being born inside, as seen by the Hubble, using first the visible camera and then the infrared camera on Hubble. So there's a little star in there making planets, probably. We'd like to know. So we will definitely be pointing the Webb telescope over there to see about planets and learn how systems like the solar system may be formed. It's not the only thing we'll be doing, but I think this is time for me to hand over to our next speaker so she can tell you how we will be using these telescopes to search for the origin of life. There we go.
Quarter at that aesthetic piece of equipment, which I'll be talking about a little later. Back to the image of, it's a real photo of a dark sky. And every star, just to remind everybody here that every star in the sky is a sun, and if our sun has planets, we naturally expect those other stars to have planets also, and they do. In fact, if you're so lucky to go out to a dark sky and ask and wonder how many of those stars that you see have planets, it turns out that it's basically every single one. Astronomers have found, statistically speaking, that every star in our Milky Way galaxy should have at least one planet. That might not be surprising if you think logically, but what is surprising is that all of these planets, they're so very different from our solar system. Our own Earth is actually extremely hard to find. And so in the short term, we have mostly found planets that are unusually not like our solar system. For example, planets Jupiter size or Jupiter mass where Mercury should be. Hot super Earths that are so close to their star that their surfaces are likely hot enough to melt rock. Planets orbiting two stars, and we have this list of incredible discoveries made by astronomers in various ground and space-based telescopes everywhere. So our own Earth twin remains elusive, but that's what I'm going to be talking about today. Now, what's most relevant for us, actually, is one of my favorite discoveries ever in astronomy and planetary science, and that is that small planets are extremely common. And this bar chart shows some of the results from the pioneering Kepler Space Telescope. It shows you on the left axis fraction of stars with planets, and it says periods less than 50 days, but that number is now increased to a couple of hundred days. On the bottom, it shows planet size relative to Earth, and the cartoon picture just reminds you, the images actually remind you of the relative sizes of Earth and Jupiter. Now, I want you to just focus on the relative heights of those bars, and if you look at the far right, you'll see that Jupiter-sized planet at 11 times Earth radii, there are hardly any, actually. Very few, compared to the bins that have these planets that are 1 to 3 Earth radii. And essentially what this is telling us is that small planets are extremely common. And we don't have super hard exact numbers for you, but it may be as high as 1 in 5 sun-like stars may have a planet that is a favorable, not too hot, not too cold, but just right for life. And in fact, when we talk about the search for life beyond our solar system, we first fixate on the so-called Goldilocks zone or habitable zone, illustrated here very roughly in green. This schematic shows you reminds you of part of our solar system. Mercury, Venus, Earth, Mars, and Jupiter, and the other planets aren't shown. And I just want you to know that in this so-called Goldilocks zone, it's not too hot, not too right, not too hot, not too cold, but just right for life. And small rocky planets are heated by their star from the outside. And so it's this distance from the star that really sets the temperature. And I just want you to know, for those astronomy buffs here, that astronomers are hotly debating the boundaries of this curve right now. What makes the planet habitable? And what the main problem actually is, it's the greenhouse gases in the planet atmosphere. Just like here on Earth, the distant planets, the exact composition and the amounts of gases will actually make the planet hotter or colder. So what we're going to do to search for planets is we want to be that may have life on them. We want to be able to look at the atmosphere to assess the greenhouse gases and assess the surface temperature, and even to look for biosignature gases, which are gases created by life that fill the atmosphere that we could detect remotely by space telescopes. And we have two pronged approach. This decade, we'll be searching for super-Earths transiting small stars. And to start with, in 2017, NASA will launch the Transiting Exoplanet Survey Satellite, TESS. This is an MIT-led mission that consists of, you can see in the image, the illustration, 4 very specialized telephoto lenses that are really not all that huge. They have big baffles, and they will have about 24 by 24 square degree field of view for each lens. And TESS will do an all-sky survey and look at hundreds of thousands of stars for thousands of planets. The prime return will be small rocky planets transiting small stars. Those are what are our easiest ones to find so far, and among these will be the closest 1,000 small stars that will be a source list for the James Webb Telescope to look at in more detail. And what the James Webb Telescope will do, it will find what now is actually a standard approach to studying exoplanet atmospheres. And you can see in the cartoon image on the left, a planet transiting the star. If a planet is very specially aligned, it will go in front of its star, as seen from the telescope. And you see a small drop in brightness of the star. We don't see any stars other than our sun spatially resolved in that detail. And the cartoon on the right is illustrating what happens when the planet is in front of the star. Some of the starlight shines through the atmosphere. And if we do it right, we can actually pick up the gases from the planet that are imprinted on the atmosphere. And we hope to do all of that, we plan to, with the James Webb Space Telescope. And what we hope to see is a spectrum that looks something like this. What this is, it's wavelength, absorption as a function of wavelength. And just so you know, for the people who aren't experts in spectroscopy, if we can't see gases in the atmosphere, if there's a cloud blocking the planet, or if there happens to be no atmosphere for some bizarre reason, this would be a straight line. So we're looking for deviations from a straight line with a special imprint that will indicate liquid water or other things. Now, about the TESS and James Webb combination, James Webb Space Telescope was not designed to actually find signs of life on another planet. And I do get asked all the time, what are the chances that the James Webb will find signs of life? And so I will answer it in 2 ways. In one way, we have to get really lucky. Every small star has to have a planet in its habitable zone, and each of those planets, most of them would have to have life, and most of that life would have to actually generate a byproduct gas that could fill the atmosphere. And the second way that I'd like to answer it, which I'd like you to walk away with, is that with the James Webb, we have our first chance, our first capability of finding signs of life on another planet. Now nature just has to provide for us. So to make sure we beat the odds, we want to follow the next approach, in parallel investing in a more futuristic way. And that way we want to search for Earth-like planets orbiting sun-like stars. We all are kind of self-centered. Here we call it terracentric. We want to find planets like Earth because in many ways, well, Earth is our only planet that we know of with life on it, and we'd like to find a replica. And in this way, we have a major challenge here because unlike the big Earths transiting small stars, the problem is extremely challenging in that Earth itself is 10 billion times fainter than the sun. And here you can see a real photograph of our sun, and that is the size of Earth, but it's not just the size that's relevant here. It's the fact that light has to go from the star to the Earth and reflect off of Earth, and for us to be able to detect that. And just to pause for a moment, I'd ask each of you if you've ever made a measurement that goes to 10 decimal places. That's like me asking you to measure the width of, this piece of paper to 10 decimal places. It's extremely challenging. And that's what we're setting out to do at NASA, Northrop Grumman Corporation, and other places around the country. So this is showing you the glare of how bright a star would be. And ideally, we'd like a way to go to space, and it's what we call direct imaging. We want to, A, get above the blurring effects of Earth's atmosphere, and B, block out that starlight so we could see a planet directly. I'm just actually going to back up and show you that one more time. Our goal is somehow we need to block out that starlight. Now this shows you we can block out the light, and then hopefully we'll be able to see other planets. And I just want you to see that we have this star shade, and the goal would be actually to block out the starlight so we can see the planet directly. And I hope you will all admire this for a moment. It's actually was really used in the desert for testing of a concept we call the star shade. So what the star shade is, its goal is to block out the starlight so that only the planet light will enter the telescope. But I hope you're all wondering why this is such a very special shape. And actually, the reason has to do with diffracted light. And this is my only professorial slide here, but I want you to be able to walk away with something that I think you'll find interesting. And that is, if we were to imagine putting up a big circular screen in space or a big square, and to block out a point source, a star, right behind that screen, we would get what you see on the top right. I think you can see rings. We wouldn't see a point source, the star in the image. We would actually see these rings. They're called Airy rings. And what it is the starlight is would be diffracting around the edge of the screen. It's the same as if we used a circular telescope. It's actually just because the waves are bending around the edge and interfering. We give an analogy, it would be like dropping a pebble in a pond. And you see ripples, those water waves. So how can we handle this when the first of those light waves is 100,000 times brighter than the planet we're looking for? Well, the answer is to have a very specially shaped screen. And you can see in the bottom left there a kind of a star-shaped. And the equivalent image you would get with that screen and a point source star is the one on the bottom right. And in this case, the analogy is like dropping a pebble in a pond. When all of a sudden, all around the pebble, it would be so perfectly smooth to 1 part in 10 billion. And all the waves would be pushed away at the very outer edges, going crazy. And that's the basic concept, is special shape to handle diffracted light so that it works to your advantage. So here's the concept of the star shade. A telescope and star shade could launch together with the petals unfurling from a stowed position and a central truss expanding and snapping the petals into place. In fact, that truss has heritage from large radio deployables. These petals have to be manufactured to hundreds of microns, and the star shade itself is tens of meters in diameter and would have to fly tens of thousands of kilometers from the Space Telescope. Right now, NASA is sponsoring a detailed study, and the team members of a team that I chair, they're all out working very hard now to put the exact details together mechanically, thermally, and the heritage story of the star shade. So we're making a lot of progress here. And there are other ways to block out the starlight from space, and we'll hear more about those in a moment from, more about those in a moment from Dan Gallagher. Oh, this was just to remind you that we want to actually see the planet directly and break up the light and to see the spectrum to look for biosignature gases and water vapor and other things that indicate that the planet would be a terrestrial planet. So to finish, I just want to show you this image of Earth. It's Earth as seen from the Voyager 1 spacecraft at 4 billion miles away. Because when all is said and done at the end of the day, to the rest of the galaxy and universe, our Earth is just an exoplanet. And so we want to find another planet to understand what our place is in the cosmos. And I want you to know that we're all here today because we believe we're very, very close in terms of technology and science and actually finding the other Earth and our chance to find signs of life on another world. Thank you. I'm now going to turn to Dave Gallagher, who's going to tell us about some of the technology being developed to do the so-called direct imaging from space.
Thank you, Sarah. It's truly an honor to be included on a panel of esteemed scientists like this. I'm very excited to be here. It's a little bit intimidating. I thought of a few jokes to make about that, but I'll limit my size. I have not been to space. I have not got my Nobel Prize in my rental car, but I'm working on it. So what you heard about here was a lot of the why and some of the what, and what could be better than searching for life in the universe? I'm going to talk a little bit about the how. The two messages I'd like to have you walk out of here with, at least on the technology side, are that, number one, this is really challenging, and number two, we have made a big investment between NASA and the DoD and others and have actually made a huge amount of technical progress. It's very exciting, and so while a lot of these things will look very hard, we've done a lot of work to get ourselves down the road to making that happen. So the first challenge, Earth is 10 billion times fainter than its parent star, our sun, as you just heard. There's a whole bunch of analogies for that, a firefly by a searchlight, but it's a really hard thing to do. And I'm going to talk first about that challenge. There's really two ways to approach it. One is external. That's what Sarah's been talking about, the sunshade. Let me say a little bit about the team. This has been going on for a while. Some of the previous and current team members are Jeremy Kasdan from Princeton, Webb Cash from the University of Colorado, Northrop Grumman, and JPL. In the top right image there, you can see a video of a pedal deployment. This was done last year very successfully. The tolerances on this are extremely tight. We're doing it. At the bottom image, you can see the inner hub with 4 of the pedals extended there. We have 9 summer students this summer at JPL who are working on actually building the deployable inner hub. That work is going extremely well, and all indications are we can meet the tolerances required. We've measured them. They're repeatable. So this is well within our capability. On this chart, rather than in the lab, this is some testing that was done out in the desert by Northrop Grumman. What's really impressive about this is this was a relatively crude test done in the desert at night with temperature variations and wind and stuff floating around in the air and rattlesnakes and whatever. And we've actually been able to demonstrate contrast ratios extremely close to what we need with the star shades. This is a small scale star shade separated by about 2 kilometers, and it really works. So, you know, the first slide was showing you how this works in the lab, that we're measuring and demonstrating that, and this is, you know, proof that again exceeded our expectations given the test conditions. So that's the external way. So now from the large to the very small, there is another way to block out the parent light, and that's using an internal occulter, also known as a coronagraph. The cartoon at the top left is a simplified illustration of our high contrast imaging testbed at JPL, where we allow scientists to come from around the world with various types of coronagraphs, or essentially masks. So when you think about that star shade on a large scale blocking the light, the coronagraph is doing it on a very small scale. And in the cartoon on the left, you can see a imperfect wavefront comes in and it bounces off a deformable mirror. There's a control loop after the beam splitter there that has that deformable mirror correct the image, and then the coronagraph mask blocks the light from the parent star. And in the middle image, you can see actual lab demonstration of a dark shadow, which is 10 billion times fainter than the central source. I won't explain in our limited time here why it's only on half the image, but that was intended as part of the lab setup. And then on the right-hand side, you can see the effect of the deformable mirror. So again, this is technology funded by NASA, going extremely well, and proving that these things are possible. So we're studying a 2.4 meter mission called WFIRST AFTA. If I had more time, I would expand the acronym. That would take about 5 minutes. This program was made possible by the generous donation of a 2.4 meter that sounds like a PBS spot, by the donation by the NRO, National Reconnaissance Office, of a 2.4 meter telescope. It's really enabled this mission, and it's under study now in astrophysics. It's going extremely well, and if you look at the 3 images, the first one is a no mask image, the second one is with a mask, and then the bottom right shows you a simulation with a planet of the mask and deformable mirror. So this will be our first chance to fly a coronagraph in space and demonstrate this. Okay, I talked about 2 challenges. The second challenge is that Earth is intrinsically very faint. I won't dwell on this. I think my co-panelists got this point across. That's a Hubble image with a planet that you can see extracted by a very crude early instantiation of a coronagraph. and then what we would need to find these Earth twins or to find an Earth-like planet, as we've been talking about, is something that's 1,000,000 times fainter than that. And when it comes to finding faint things, it's a very simple algorithm. You need bigger telescopes, you need more collecting area. James Webb is leading the way in increasing the collecting area. As you've seen, it's our biggest telescope yet, and mirrors are built. Everything appears to be working perfectly, and we're well on our way to success in 2018. The search for life is going to require even larger, lighter space telescopes. So you can see the evolution from Hubble to James Webb to an artist's conception there of a 16-meter space telescope. In green is the ratio of the launch mass to the collecting area of the telescopes. So the message is you got to get bigger, and to do that you got to get lighter. One of the ways we do that is with very lightweight replicated optics. Sitting over there in the case is what's called an advanced hybrid mirror. Northrop Grumman has built, that's about a 1.2 meter hex segment. These are lightweight silicon carbide mirrors that are actuated and have a very, very fine nanolaminate foil across the top, kind of the composition of heavy aluminum foil. These have been built, proved out, the technology matured up to a very high level and essentially ready to go. At last, expanded there for you is just to show you a couple of concepts for larger space telescopes. There's a 9.2 meter and a 16.8 meter version. Those are being studied. There's a lot of promise in both of them. You can see a lot of large deployments required, but we'll have a lot of confidence because of the work done on James Webb as well as the technology work being done now. And then finally, there are some really far out concepts. Ball and DARPA are working on essentially a 20-meter membrane telescope that looks very promising, and it's essentially got an etched diffraction pattern on the membrane, and that's been demonstrated at subscale versions in the lab. Thank you very much. I'd like to turn it over now to Matt Mountain.
So let's bring this to conclusion. So here is the challenge before us. How do we find Earth 2.0? As Sarah's told us, we already know that our galaxy has at least 100 billion planets in it. And we didn't know that 5 years ago. Just think about that. 5 years ago, we couldn't have actually put those words on this chart. That's what Kepler and NASA has done for us. We actually know now what life might look like. We know life can actually imprint itself on the atmosphere of planets going around other stars. This is what a living planet looks like. We actually know where all the stars are. Here are all the stars nearby to us within 200 light years. This is every single star within 200 light years of the sun. We actually know how many stars live a long time, between 5 and 10 billion years. That's where we have to look. It took 4.5 billion years for us to arrive here. We actually have done the census. Kepler has actually done the census of how many planets there might be in our galaxy. And what we've learnt is remarkable. Between 10 and 20% of stars have Earth-like planets, or at least Earth-sized planets, in that amazing zone called the habitable zone, the Goldilocks zone. Not too hot, not too cold, just right. So, let's take those statistics, take that census data, and let's do the discovery. Here are all those stars. We can now apply those statistics and ask how many stars can we see with a 5-meter telescope, roughly the James Webb. Apply those statistics. What you see on the right is how many stars the James Webb or a telescope like it. Very few. How lucky, as Sarah said, do we feel? With 10 meters, we can peer even deeper into that cloud of stars. We can go deeper and we can separate out and see even more planets. And with a 20-meter telescope, we can see hundreds of Earth-like planets around other stars. That's what it takes to find life. Of course, this is a hard problem, but NASA's been very good at doing these hard problems. NASA's ability to launch great telescopes like the Hubble and soon the James Webb. It's going to do anything. Here we go. Oh, all right, we'll stop there. There we go. That's what, but to actually, and we may find liquid water. We may be really lucky. But to find evidence of actual life is going to take another generation of telescopes. And to do that, we're going to need new rockets, new approaches to getting into space, new approaches to large telescopes, highly advanced optical systems, as David and Sarah have showed us. But between us, between science, NASA's technology, and today's space enterprise, it's within our grasp for the first time in human history to make a discovery that will change the world. Or to plagiarize Steve Jobs, a discovery that will put a serious dent in the universe. Now, if we can get a telescope into space of the sufficient size and get it launched, imagine the moment that the news breaks we've discovered Earth 2.0. Imagine the moment the middle school kid who looks up from procrastinating about his math homework, my son, or her math homework, but realizes that he or she could be the person who could design the rocket engine that could take a starship to Earth 2.0. Imagine the moment a biology teacher, struggling to engage her high school class, realizes that tomorrow she could tell an amazing story. For the first time in human history, we have reached the point when we can look out to the stars and realize the miracle of life has occurred elsewhere on a planet going around another star. Imagine the moment the whole world wakes up to the news our long loneliness in time and space may have ended. We may no longer be alone in the universe. Now, each of us, every day, have much more immediate concerns. There's so many problems here on Earth we need to deal with today. How will I get my project finished? How will I get that next contract? How will I pay college for my kids in this economy? Do we even have the space infrastructure for our own national security or economic security, let alone looking for life elsewhere? I have deadlines to meet. Do I really have time to think out of the box? Could we use those technologies those crazy scientists want for other things? How do we do audacious things in space again that inspired the generation of people sitting before you? And what is our legacy actually going to be? And while you reflect on what we've all said here today, we wanted to finish on some words from Carl Sagan.
What new wonders undreamt of in our time will we have wrought in another generation and another? How far will our nomadic species have wandered by the end of the next century and the next millennium? Our remote descendants, safely arrayed on many worlds through the solar system and beyond, will be unified by their common heritage, by their regard for their home planet, and by the knowledge that whatever other life may be, the only humans in all the universe come from Earth. They will gaze up and strain to find the blue dot in their skies. They will marvel at how vulnerable the repository of all our potential once was. How perilous our infancy. How humble our beginnings. How many rivers we had to cross before we found our way.
So imagine the world. We've gone from Galileo, Hubble, Spitzer, Kepler, enabled by NASA and their partners. What's it going to take to cross that next river? It's going to take a partnership that's led to the James Webb Space Telescope, a partnership that may be able to lead to other telescopes. Putting together the partnership that can find Earth 2.0 is a challenge worthy of a great generation. Thank you for listening to us. And Ellen, over to you.
That was truly amazing. And we do have a fair amount of time for questions. And I want to remind our audience who's out there to send us questions at #AskNASA. But I'm going to take the moderator's prerogative here and ask the first question. We're often the most surprised in science by things that we don't expect. For example, the arrangement of planets around stars, Kepler, all the work we've done, it's totally turned our views of how solar systems form sort of upside down. Where do you, and of course I'm asking about an unknown here, but where do you think the really big surprise is going to come in TESS or JWST? What are you sort of saying, I bet something cool is going to come from there. What are you thinking?
I'll start by just saying right now, we've, just like a lot of other sciences, astronomy and exoplanets in particular is moving into a big data regime. And so essentially we don't totally know what the next thing is. It'll be the new discoveries and it'll be the statistics, the having lots of the same object, knowing how many numbers there are and what their distribution is. I think our hope is actually, just speaking scientifically, in addition to looking for other planets that might be like Earth, because we're so fixated on that, it's just really understanding planet formation. You have to understand that for generations, we thought we would have a Jupiter far out, where our Jupiter is. The big giant planets would be far from the star, and that smaller terrestrial planets will be close in. And so I would say that planet formation theory has been turned on its head, and only with more and more data covering all the regimes of planets possible can we start to understand planet formation in detail.
Great. Okay, we do have a fair amount of time for questions from the audience. So, questions, please. Right down here in front. May will grab you.
Lynn Lee for SpacePolicyOnline.com. In the search for looking for Earth 2.0, is there a specific number that you're looking for? And if you find more than one, what would be the scientific criteria that would weigh most in determining which to focus on?
Well, the reason why we showed the many different sizes of telescopes is we believe that this will be a multi-generational search. As I mentioned, with the TESS and James Webb Space Telescope combination, we have a shot at finding something interesting. And then our next generation would be our, say, 2-meter class telescope, for example, or a little bigger, where we will look at the nearest, say, 20 to 100 sun-like stars. And we hope that we would find a few to study. In the more distant future, when we want to have handfuls of them, so we really have the chance to find a sign of life, and we can be sure, because in any one case, we might not be 100% sure. We may say, oh, that planet has maybe 80% chance of that signature we see is from life. That one may have 99. But to have enough to really, really, truly believe and have enough to actually study in detail will require the futuristic space telescope that we don't have plans for yet, that we all showed you maybe in the 10 to 20 meter class. So it's actually a graduated approach.
I mean, another way of saying this is, we have no idea. We know how many Earth-like planets are. We think we know how to characterize the atmospheres. But there are 10 to the 22 stars in the known universe. That's one with 22 zeros after it. And some people believe life is everywhere. That's one. Some people believe we're completely unique. That's 1 part in 10 to the 22. That's a really big error bar, even by cosmology standards. And the only way we're actually going to find that out is to make a measurement. The way astronomy has always proceeded is we make measurements and we're then surprised. And so by making that measurement, we don't know if we're finding 1, 2, or 3, or 0.
And the real question, just to follow up, because you've asked a really central question, and to quote another great philosopher, do you feel lucky? Yeah. The amazing thing from where we sit today, and it's from the Kepler telescope, is, and Sarah described it very eloquently, when you look up at the night sky at night, we now know that virtually every star has a planet around it. In fact, most stars have solar systems around them. And so the idea that we're going to find planets that are very much like Earth, I think is a very high probability. The question is, how hard is it for life to get a foothold? How hard is it for life to start? And that's where we really have no idea, and where I think the discovery of a planet like Earth with signs of life on it will be so remarkable. That will be our first scientific evidence, that life might be elsewhere, even primitive life.
Next question.
Hi, Eric Neeler, Discovery News. When you turn this thing on, when you turn the web on, do you have an idea of where to look first, or are you just going to go fishing?
Oh, well, maybe I should take that. We will have a very detailed plan before we turn it on. Right now, we haven't argued it through. Clearly, there's a tension between wanting to make sure that all the pictures are beautiful and making sure that they're very scientifically important. I showed you the the Orion Nebula, where we know that stars are being born, and every telescope is always pointed when it's new. I'm sure we'll look over there. We will look at the most tempting targets right away, as soon as we think we're able. And there will be many.
There's a question.
I just wanted to add one thing that...
Go ahead.
Oh, before you start, I just wanted to add one thing, that in terms of which stars and which planets we're going to look at, what's interesting is there's relatively a democratic process where members from the astronomy community will put in proposals, and time will be awarded by a committee of people from the community themselves. So in this sort of shuffle, the best candidates will definitely rise, and multiple people will propose to study the same object. So it will happen.
Excellent presentation and amazing work that's been done. I'm sure there's going to be even more progress made. But my takeaway from this is that your endpoint, in terms of saying is there life or not, basically are signatures in the atmosphere, biology occurring. There's nothing really more specific than that. I mean, obviously people want to know, is there intelligent life out there? If you had a system that, for instance, would be able to discover or be able to observe electricity or incandescent light, incandescent electrical energy, that would also be very exciting. But the way I think you've presented it is it's basically you're looking for biological signatures generically. Is that correct?
Yes, I want to add that we are looking for biological signatures, gases that are produced by life, gases that don't belong in the atmosphere, that, like our own Earth, we have oxygen, which fills our atmosphere to 20% by volume. But without plants and photosynthetic bacteria, we basically have no oxygen, except in some unusual circumstances. What you're talking, we often refer to as technosignatures, signatures that there's, people or creatures on another planet that can generate a signal that's not naturally occurring. People have studied that in a lot of detail, but it's just too hard for our first-generation space telescopes. Those signatures are super small and very narrow and very, very weak. So we hope that someday, a much later generation, will actually be able to see those things and follow up on what we have first found.
Okay, let's go to some questions from social media.
Sure, this one is a popular question here. It comes from James on Twitter, who asks, if and when life out there is discovered, will the U.S. government actually let the people know?
Sounds like a good chief scientist question.
Of course we would. That would be so amazingly exciting. And at NASA, our policy, whether it's data coming back from Mars, data coming back from Kepler, we try to get it out to the public as soon as we can because we want everybody to share in the excitement of discovery.
Okay, our next question here comes from Brian on Twitter, who's asking, are you looking for intelligent life or living single organism bacteria?
Well, in fact, we believe that we don't know what will be generating that byproduct gas. It might be some kind of sophisticated life. It may just be single-celled bacteria. And by the way, thanks for asking that question, because we forgot to specify here. We're looking for whatever's out there that's generating gases that don't belong in the atmosphere. There's a separate approach that we didn't talk about today, SETI, Search for Extraterrestrial Intelligence, and I think you can believe that if we find any signs of life via these biological gases, other people with other techniques will be following up in any way.
Okay, we'll take another from social media.
Indeed, wonderful here. This question is regarding the star shade here. It comes from Katrina, who asks, how does the star shade move away from its telescope and stay in relative position? I didn't see any thrusters in the animation.
Yeah, it's essentially, think of it as a separate spacecraft. While it could be launched together, it has to formation fly. It's not as challenging as you might think, but it's going to be out thousands, tens of thousands, potentially 100,000 kilometers away, but it has to maintain a relatively straightforward stability that's well within the state-of-the-art right now for its guidance, navigation, and control.
Right, and I forgot to say at the end of my presentation that the object back there in the corner, it's a prototype petal, one that was shown in one of the pictures. And so I guess we need an animation in the future that shows the spacecraft bus with the thrusters and other things that actually the star shade is attached to.
Let's take a few questions in the room before we go back to social media. Go ahead.
Mm-hmm. I can talk? Okay. Well, thank you very much. I have a question. Have you thought about using the sun as a gravitational lens or using an array of a small telescope instead of a really big telescope?
Can we take that? I mean, one of the problems is pointing towards the sun is a really bad idea. We go to an awful lot of trouble to keep the Hubble away from pointing at the sun because the sun is really bright. So it's a really dangerous undertaking. You'd have to think it through, though people have looked at this idea. The problem with the array of telescopes is it gives you the angular resolution, but it doesn't give you the collecting area. We're trying to solve two problems. One, how do you separate the star from the planet? That's where an array of telescopes can work. The other problem is, how do you detect something which is fainter than the faintest galaxy in the Hubble Deep Field? And there, a distributed array is no good. You don't get enough photons. So you actually need both a big telescope and a big collecting area so you can actually detect this really faint thing next to this really bright object. It's a very hard problem.
I think I saw a hand. There was another question back on this side.
My question is, what words of inspiration can you offer future generations that are going to lead the journey to find Earth 2.0?
Go for it, Joe. Well, I think the first thing is if you look at us up here on the podium, this is not going to be our telescope. We're the age of the Hubble Space Telescope. You haven't known a world without the Hubble Space Telescope. The next generation, which is going to be very exciting, and a telescope you may use someday, and I know Sarah will use, is the James Webb Space Telescope, and that gets us very close. And who knows? Maybe we're very lucky. But that next generation telescope involves technology. It involves a lot of hard work and the things that we've talked about. And that's something that you can be a part of. In fact, maybe the critical inventor for the optics or the technology, the electronics, or the wavefront sensing and control that will enable such a rocket. Or how are we going to package a 20-meter telescope into a smaller rocket? Perhaps even the astronaut who will assemble it in space.
Another way of saying that is if you want to work on something really hard, really complicated, that will change the world, this is the project.
Before we go to the next question, we have a question up here, but before that, I just want to remind people to be following us at #AskNASA and get your questions onto there. Now, go ahead.
Yeah, all these great telescopes have international collaborators. What's going on elsewhere overseas, great telescopes that don't have NASA as the lead partner? Or do they all involve everybody since they are so expensive?
Well, really, the observatories that we've built, the great observatories, Compton, Hubble, Chandra, Spitzer, have been international collaborations. And the James Webb Space Telescope, with our partners with the European Space Agency and the Canadian Space Agency, are wonderful examples where the world has come together. And the U.S. is the leader in large space telescopes and space astronomy, something we're very proud of. But we're even more proud that we've always done it in partnership, and I think that is the wave of the future.
Before we go to the next question, I'm gonna insert kind of maybe a sticky question that Sarah brought up a little bit earlier. When we look for life in our own solar system, we're really focusing on Mars because Mars maybe at one point was in that habitable zone. We think Mars is the most likely place where life could have developed here in our own solar system. But also in our solar system, we really want to go to Europa and find out, is there life under that icy crust on Europa? We look at places like Enceladus, like Titan, not really in a conventional habitable zone. And Sarah, you mentioned the fact that habitable zones are a little bit hard to get your head around.
Right. Well, in exoplanets, we're only focused on what we can see by remote sensing. And so if there is a Europa-like world, let's say a water world, where an ice-capped planet that has liquid oceans underneath, we won't see signs of life on those. But we're not worried about it because stars are plentiful and planets are plentiful. And so we believe that the right combination is out there for us.
And I'll just add that we're just on the cusp of releasing an announcement of opportunity for instruments for a future Europa mission. And so for the listeners in the audience and on the web, stay tuned very soon.
I think there's a question down here in front.
Yeah, I was just curious, all the excitement of people now looking for life elsewhere, was there a point in the scientific community, was there a discovery that sort of turned people's scientists' minds to saying, I really do think there's more out there, we're not alone? Or did different scientists come to it through different discoveries, or was there one, sort of tipping point?
Well, I'd like to say there was one tipping point. If I may, we talked a bit about transiting planets, when planets go in front of the stars seen from the telescope. Well, a number of planets had been discovered, maybe 30 or 40, by a different technique called the wobble method. It's not so relevant. And we started to understand as a community that planets could be quite plentiful and in all sorts of crazy orbits. But there were many people, because in science we're supposed to give each other a hard time. It's our job to, when there's a discovery, push back and make sure it's real. And there's a large part of the community, probably most of them, who believe that the planets weren't planets, it was some effect of the star. And so I believe a defining moment was when two independent planet-binding techniques saw the same planet. And it was basically incontrovertible that, yes, planets exist around other stars other than the sun. Yes, planets are in unusual orbits. And wow, we could find something so challenging, the universe is now open for us.
I think there are 2 points. One, and Sarah was actually responsible for this, one was we realized that planets did transit, but then we also realized from space, and this is something we never anticipated, first with the Hubble and then with Spitzer, was that we could actually measure the gaseous constituents of exoplanets, big Jupiters, but we actually could see methane and oxygen and sulfur. Couldn't see that before. And the second breakthrough was the realization with Kepler that there are 100 billion planets out there. I mean, as I said, 5 years ago, we couldn't